We have seen that the temperature strongly influences the performance of a PV module. However, while the level of incident irradiation and weather conditions can be easily measured, the temperature of a solar cell inside a PV module is hard to evaluate without compromising the integrity of the module itself. In this video, we shall introduce three models to evaluate the temperature of the PV module. They differ in complexity and accuracy. Let's start with the simplest one, based on the so-called installed nominal operating cell temperature, or INOCT model. This model is based on an estimation of the average cell temperature by means of the nominal operating condition temperature. As we have already seen, the NOCT is a parameter provided in the datasheet. However, in order to take into account the mounting configuration of the PV module, the installed nominal operating cell temperature was defined. The INOCT is described as the cell temperature of an installed array under NOCT conditions, and it depends on the different mounting systems and material used for installation. Three main mounting configurations exist: direct mount, standoff with a distance W from the rooftop, and the rack mounting. Basically, the differences lie in the distance between the module and the underlying structure. Then it is possible to model the so-called INOCT value as function of the NOCT based on the configuration. Usually, the closer the module is to the underlying surface, the higher the INOCT is. Note that in the standoff case, the variable x is inversely proportional to the distance w. The INOCT model is based on a trend found in empirical data for a number of PV systems located in a specific climatic area. In particular, it was observed that the temperature of the module rises almost linearly as the solar irradiance increases. Thus, by interpolating all the scattered data, it is possible to come up with this equation, where the module temperature depends on the ambient temperature plus the ratio between the observed and the NOCT irradiance multiplied by the INOCT temperature, as obtained before, minus 20 degrees, a value that offsets the ambient temperature. In this formula, the influence of wind is not included, and this aspect considerably simplifies the model. Therefore, Duffy and Begman proposed a tweak on this empirical model, which is basically a correction accounting for the presence of wind. So, in this second thermal model, next to the basic equation, a factor was added that is a function of the wind speed, indicated with the small w. Then we have the efficiency of the module at STC and the tau times alpha, where tau is the transmittance of the front layers of the module and alpha is the absorptivity of the module. Hence, the product gives the fraction of incident light that is absorbed by the solar cells. Usually, the product tau alpha is assumed to be 0.9. Reality is a little bit more complicated than what the two empirical models describe. As a matter of fact, the PV module temperature depends on ambient temperature, tilting, irradiance, wind speed, sky temperature, ground temperature, and the ambient in which the PV system or module is installed. All these aspects are not taken into account in the INOCT and DB models. So, to accurately evaluate the influence of external meteorological parameters, more involved models are used. The third thermal model we present here is the Fuld Dynamic model, or FD model. This is based on a detailed thermal energy balance between the module and its surroundings, including a radiative, convective, and conductive heat exchange. This model reveals the physics of heat exchange characterizing the temperature of PV modules under illumination. This is a first-order differential equation that takes into account the three types of heat transfer between the PV module and the surroundings. First, we have the heat received from the sun, where phi is the absorptivity of the module. The second term expresses the convective heat exchange with the surrounding air from the front and the rear sides of the module. And HC denotes the overall convective heat transfer coefficient of the module. Lastly, these two terms represent the radiative heat exchange between the rear surface and the ground, and between the upper module surface and the sky, respectively. Here, E top is the emissivity of the module front glass, and E back is the emissivity of the back. These last two data about emissivity are usually given data, or they can be calculated, while the absorptivity can be found in the literature, and sigma is simply the Stefan Boltzmann constant. It is important to note that the conductive heat transfer between the module and the mounting structure do not appear in the equation, because the contact area between the module and the ground is so small that can be neglected. We want to point out that we assumed the entire module to be a single mass with a uniform temperature. However, this assumption is not entirely realistic, because PV modules are made of various layers of different materials. Our purpose is to evaluate the temperature of the solar cell itself, which is where the solar radiation is effectively absorbed. This temperature will be higher than the temperature of the surface module, because of the heat produced in the cell due to light absorption. However, our uniform temperature approximation is justified because the solar cell has a relatively low thickness compared to the EVA and to the glass layers, and also its heat capacity is lower than that of the other layers. This results in a very low thermal resistance of the cell. Another assumption that we are going to use is that we consider a steady state situation, while in reality the temperature follows an exponential decay, lagging behind the variation in irradiance level. However, the time constant of a PV module is generally in the order of about 7 minutes, meaning that after a step change in irradiance, the module will take around 7 minutes to reach 63% of the total change in temperature, as demonstrated in the paper mentioned below. As a consequence, for time steps exceeding the time constant, for example 10 minutes, the module can be approximated to be in a steady state condition. This assumption allows to get rid of the differential term on the left-hand side of the equation. So, now that we do not have to deal anymore with the differential equation, we can expand the two binomials to the fourth power in linear binomials, which are much easier to use. By rearranging the terms, the equation can be explicitly expressed by this formula, where the radiative heat exchanges are functions of the module temperature, and hence the equation must be solved iteratively with an initial guess. Before we can solve it, there are still some unknown variables that must be determined, such as the convective heat exchange, which is a function of the module dimensions and wind speed, and also the module absorptivity, which is defined as the fraction of the incident radiation that is converted into thermal energy into the module. This value is linked to the reflectivity R and efficiency of the module by the equation depicted. In this last slide, we compare the reported three models by plotting the temperature of the module as function of the wind speed. As you can see, the NOCT model does not show any change because it is independent from the wind speed. The Duffy-Beckman model, which introduces wind dependency, trends quickly towards lower values, overestimating the wind effect. Finally, the Fuld Dynamic model is gentler in the decay and gives a more realistic estimation of the module temperature. To conclude, the NOCT and the DB models constitute two extremes and are easy to use, while the highest accuracy is reached with the Fluid Dynamic model. The downside is that this last model is also the most complex. At 3 meters per second, even the step indicating the threshold between turbulent and laminar flow is modeled with this model. After 3 meters per second, eventually air turbulences and vortices are generated on top of the surface, thus accelerating the heat exchange, resulting in a sudden drop of the curve. In the next video, we will start to talk about all the issues related to mounting.